Okay, so hello everyone, welcome to Modern Semiconductor Devices for Integrated Circuits lecture number 15. Actually, we are going to revise the lecture contents 14. So let's start. So remember, we have started with this PN junction, and one of the features of this PN junction is under zero bias, depletion region is formed automatically. So this is my depletion region, which is automatically formed the moment we connect P and N together. Okay. Now this side of the PN junction consists of positively charged immobile ions. This contains negatively charged immobile ions. Is it not? And this is my width of the depletion layer. Now, if I apply an electric field, the internal electric field will be directed in this direction. Why? Because you have an internal built-in potential. So that built-in potential has a polarity as shown over here. This is positive, this is negative. So this is the polarity of the built-in potential. So because of this built-in potential, you have this electric field, which is called as internal electric field. We call it built-in electric field. So basically, we have to derive the formula or how this electric field looks like and the expression also. And then what is the formula for W, what it depend upon, and also the potential, how the potential is varying. Now, energy band diagram we have studied is varying like this, right? Yes or no? For PN junction, its variation is like this. This is energy band diagram where you're plotting energies. If you want to plot potential, then it will be reverse. Why? Because energy and potential, what is the relation? Q, right? So Q have a negative charge. So if energies are going like this, my potential will go opposite like this. Agree? Okay. Now let's concentrate over here. Now, this region over here, which is away from the junction, is called as neutral region. Neutral region where there are no electric field. Electric field is present only in the depletion region. Okay, because there are immobile charges over here. Here is also a neutral region. So what we call this as x equal to 0, metallurgical junction, where the actual P and N junction meet. This is called as minus xp. This is called as xn. Obviously, to the left hand side of x equal to 0 is negative axis, right? xp means on the distance on the p side, and xn means distance on the n side. So 0 to xp minus xp and 0 to xn is my total w if I combine both. So xn and xp will be w. All right. So if you see, the first diagram is the built-in charge, space charge. We call it space charge region or depletion charge. So this is the collective charge. So what we are assuming is, we are assuming that there is an abrupt junction. What do you mean by abrupt junction? Suddenly the this thing, the doping concentration changes suddenly like this. Yes or no? So this is abrupt junction. Graded junction will be changes smoothly like this. So we are using uniformly doped abrupt junction analysis. So here this is a positive charge, right? Accumulation of positive charge, and it's not moving. It's like trapped. So this is accumulation of this charge is represented over here. This is space charge. Okay. And here you have negative charge, immobile negative charge, that is represented below. Are you following? Yeah. So this is versus x, the distance x. Okay. Rho of x. This is built-in space charge. And next is my electric field. This is my electric field. Now, how do you get this electric field? If you integrate this, you'll get this. Integration of a constant is a straight line. You remember? So here it is. This is positive. So this will go down, and this is negative. This will go this direction. And you will have a maximum electric field. And why the electric field is 0 over here? Because they are neutral regions. Electric field is only present in the depletion region, not over anywhere else. So you can refer to last lecture's recording for more details. I am explicitly discussing this. So this is how the electric field will look like. We have to derive the expression also. And then this is the potential, the way I have shown you now. This will be the potential. And you know what is the potential in a built-in potential? This. If I multiply it by Q, it will become potential energy, built-in potential energy. All right. So what are we doing is, we are going to derive the expression of electric field and this potential. And also we will derive the expression for W, which is depletion region width and space charge width. All right. So first of all, we have to define the following assumptions: that PN junction is uniformly doped, it's abrupt junction and under zero bias. We will derive built-in electric field, depletion region width, and peak electric field formulas, expressions. So assumption is P and N region far away from the junction are neutral, field free. Electric field it doesn't present over there. All donors and acceptor are ionized, meaning what? Every phosphor atom will readily give away its fifth valence electron easily. And similarly, boron atoms. Depletion approximation, meaning I have not taught you depletion approximation. It means that depletion region doesn't contain any mobile carriers. It is depleted of charge carriers. Carriers which cannot move are present, but carriers which can are mobile are not present. So that's the meaning. Depletion region means depletion region is free of mobile carriers. Mobile carriers are not present. All right. So we went ahead with the derivation. We started with a Gauss's law. This is Gauss's law. You must have encountered this in physics. dE by dx is rho by epsilon. This is permittivity. And rho is the space charge, right? And E is what? Electric flux, electric field minus d psi by dx, where psi is my potential. Yes or no? Now, it shows that the electric field is caused by the potential gradient. Now, don't write it right now. You can cover it later. I'm not revising it. So we are deriving the formula for the electric field. So electric field created in the depletion region by the separation of positive and negative space charge densities. Because you have a positive and a negative charge, there will be electric field present. All right. So the built-in electric field is determined by Poisson's ratio, Poisson's equation, one-dimensional Poisson's equation. What it is? D square psi of x. Psi of x means it's a function of x distance. Upon dx square is minus of rho of x upon epsilon s. Okay, this is a permittivity. That is equal to dE of x upon dx. So this is my Poisson's equation, is the starting point. The various quantities are written over here: electric potential, electric field, space charge density, permittivity of free space, and all. Okay, so this is the starting point. Now, what will be this? See, this side we have all ND, N region, na? So N region has concentration of doping is ND. Why we are multiplying with Q? By charge, total charge we want, na? So total charge will be Q into ND. Similarly, over here it will be minus Q into Na because the immobile charge is down. Understood this? Now, the charge density in the depletion region are, so rho of x is minus QNA from minus xp to 0. See, from minus xp to 0 it is minus QNA. From 0 to xn it is QND. That is what is written over here. Equation number 2 clear? Now, electric field in P region will be, electric field if you want to find out, it will be integral of rho of x upon psi s. Yes or no? Because see, this is the relation. Now, if I want electric field, I have to integrate. To remove the derivative, I have to integrate, right? So E of x will be integral of this. Getting it? So I am integrating it. Basically, I am integrating this region. So integration of a constant will be a straight falling slope. So integration of this will be this. On the P side, let's concentrate on the electric field on the P side. So P region will be minus Q Na dx by psi x. So here everything is a constant except distance. So integration of d of x will be x plus constant of proportionality. Now we have assumed a depletion approximation. So electric field is 0 in the neutral region. That means x is very, very small. For x very, very small compared to xp, we put e equal to 0 to find this C1, right? C1 find karna hai na in the proportionality constant. So we substitute it over here. Put e equal to 0 at x equal to minus xp. If we substitute that, you will get C as follows. And when you substitute C1 over here, you get the expression of electric field as follows. Q minus QNA x minus xp upon psi x. You can write this down at least, only this expression, if you are not present last time. If you were present last time, then it's okay. So electric field at P side is minus QNA x plus xp upon psi s. This is the permittivity. What is S? Permittivity of silicon.
So,
Yeah.
is the permittivity for silicon the same as that is which is used in like other?
No, it's different. In fact, the permittivity of silicon is different. Silicon dioxide is different. Metal is different.
But if even if we use like pure silicon for other applications as well, it will change at this.
Yeah, depend upon the material, how pure the silicon is. Actually, we are deliberately making it impure by adding the dopants.
And that will affect.
That will affect.
But
So there are materials fixed characterization of this permittivity levels. These are constants. These are available. And where do they come from? From the actual manufactured device. There are equipments to measure the permittivity. So, yeah. Similarly, electric field in the N region will be same analysis we'll do. Now we substitute Q and D. Okay. So we get En, electric field at N side will be Q and D. Write this down. X minus Xn upon epsilon S. So this is valid between 0 to X, going from 0 to Xn. Okay. Written? All right. So what are the learnings from here? We are finding the maximum electric field. So where is the maximum electric field occurring? It occurs at the metallurgical junction over here. See here. It happens at metallurgical junction at x equal to 0, which is nothing but EM. EM stands for maximum electric field. Now we are finding the expression for it. So we substitute x equal to 0 in the formulas we have written just now. So what do we get? EM is minus QNA dot XP upon X epsilon S and minus QND upon epsilon S into Xn. All right. So this is my maximum electric field formula. Okay. Now from this, can we equate these two equations? Q and epsilon S will get cancelled. So finally we get Na. Why we have written mod? Because distance cannot be negative. We have taken just a reference. So Na xp and dxn are equal. What does this signify? This has a very important significance. It signifies that, let's say if I have a Pn plus junction. What do you mean by Pn plus junction? Mean doping level in P's n side is more. To doping level in n side is more means what? The distance from 0 to xn will be less. So it's inversely proportional. If my doping at this level is high, my distance will be low. Are you understanding? So that means lightly doped silicon is having more distance. Depletion region distance is more, extended more. Okay. So the depletion region penetrates primarily into the lighter doping side. This will be very, very handy when we discuss the heterojunctions and heavily doped PN junction. You know what is a Zener diode? Heavily doped PN junction only. Okay. So this states that Xn and Xp are inversely proportional to the doping concentration. All right. So write down the formula for EM and write down this expression number 9 and 10 actually. Please write them down. Okay. And then after writing this, draw that doping profile and electric field. I'll show it to you. Wait. Completed? We can have numericals on this also or conceptual one. Fine. So you need to draw this. So first diagram is space charge versus distance, and second diagram is electric field versus X. Please draw this profile. So how do we get this curve? By integrating this. By integrating this, we get the electric field. Can you tell me why is the electric field in the negative direction? Because in the P region, we have negatively charged ions, and in the N region, we have positively charged ions. And electric field is always directed from positive to negative. So that's why it's reversed. That's why negative. The slope of this line will be, can you see this? This is the integral. Na? E you get by integrating this, right? If you integrate this, you will get this expression. So dE by dx is the slope, right? This is given by minus qa upon epsilon s. So this is the slope, and this is the slope. What will happen if xn and xp are not equal? You will get an unequal electric field. Yes, correct. So you might get an electric field which is like this. So you have metallurgical junction. One distance is larger than the other distance is smaller. So we can get this electric field also. Are you getting it? This will be xn, this will be minus xp. So this is also possible.
So, do we need to like correct for that when making a device, or is that, or like this pattern not acceptable for building something?
Is it?
Like, can we apply, like even if you have like an irregular electric field, is that like is it
We are
good for?
assuming a uniform doping.
So is it
So
good for
uniform
like
doping, and we are assuming that neutral region have a no electric field present. So this is under tremendous approximations. So what you are saying for a regular structure, if you remove this approximation, then the electric field won't be like this. So under these observations, under these assumptions only it will work. Now, tell me, everyone, now we have derived the expression for electric field. How will you find potential psi of x? Phi of x, for how will you find? Integrate. If I want to remove this, integrate. So you have to integrate this expression now. Are you getting it? Yes or no? So let's start for today's topic. So we'll write down, we'll derive. Now let us write derivation of psi of x and w for p-n junction. Okay. Acha, what were the features of this electric field? This electric field is directed in which direction? This direction. So this built-in electric field is directed from N to P region. For uniformly doped PN junction, electric field is a linear function of distance. And देखो ना, linear function of distance ना. This is the second feature. Third feature is its maximum value happens at x equal to 0. Okay. The fourth feature is the depletion region. The built-in electric field only exists inside the depletion region. That's it. Okay. Is this, now I can ask you a question, is this electric field present even without application of any external voltage in a PN junction? Is this electric field present inside the PN junction even when you apply a zero voltage to a PN junction? Yes, because this is internal electric field. All right. Okay. So let's start with the derivations now. So write down. Um, we know electric field is given by minus d phi of x upon x d, yeah, partial derivative. And then that means if I want to have a potential as a function of distance, it will be minus of integral of e of x dx. Yes or no? So let's derive it for p region. It's visible for you all, no? Okay. Let's derive it for p region. So we'll write in p region phi of x is equal to minus of integral of e of x. What was the formula for p region? Minus na? Minus qna. So minus minus will get cancelled. You will get qna upon epsilon s into x plus xp. You have written this formula, right? You have to integrate this. Now you have done mathematics. You can help me out in this. So phi of x will be qna epsilon s will be a constant. What is the integral of x? X square by 2. And what is the integral of dx? X. So this will be xp into x, right? Plus constant of proportionality. Because you don't have a limit, right? Now, can I say at x equal to minus xp, my potential is 0? How?
Yeah,
Why?
because
Electric field is not there at x equal to. See, what we are saying is electric, this is my PN junction. This is x equal to 0. Let's say this is minus xp and this is xp. What we are saying is in this region, what is this region?
neutral.
P neutral. So this is my P neutral region and this is my N neutral region.
Okay.
Over here, my electric field is not present. So if electric field is 0, can I say integral of 0 will be 0 only? No? Are electric field is 0 where? From here to here. I'll tell you. Wait. Electric field is 0 from here to here. This is P side. This is N silicon. Right? So electric field is 0 over here. So here electric field is 0. Inclusive at x equal to xp. समझ में आया? X equal to minus xp and at x equal to xn. Okay? So it is 0 for x less than minus xp and equal to x greater than or equal to xn. ठीक है? When is the electric field non-zero? For x less than xp. So it is E is not equal to 0 for x greater than or equal to minus xp and sorry, equal to nahi, greater than. Means from here to here it is there. And then and x less than xp. Means electric field is present only in this depletion region. Alright? So that's why we can write it over here at x equal to xp, phi of x will equal to 0. That will be equal to 0 equal to qna upon psi s xp square upon 2 minus xp square. We are substituting x equal to minus xp plus C3. So what is C3 now? Anyone? Yeah, qna upon xp square by 2, but qna upon 2 psi x into xp square, correct? Now we put that over here, we substitute this over here, so we get this is at p side now. At p side will be q na epsilon s. 2 we are taking out, so what do we get inside? X square plus 2 xp into x plus xp square. You know what I have done? I have taken q and a upon 2 psi s common outside and I've added all the internal terms. Did you get it? After substituting it over here. Or should I write one more step? You have understood this? Check. I've skipped one step. I've taken q and a upon 2 psi s common. So inside I'll get x square because 2 is outside. Got it? So what is inside term? A square plus 2ab plus b square. Correct now? Yes or no? So what do we get? X q na upon 2 psi s. This is x plus xp the whole square. This is quadratic, right? So this is my potential valid between minus xp. Yeah. So call this equation number. I mean, last time what was the equation number we have done? Let me check once. 10. So this is 11. It's a continuation from the previous lab topic. So this is at what side? At P side. Similarly, you have to do it at N side. Okay, let's do it. It is clear now why what we are doing actually, it's falling in line. Anything you have incomplete? Can we move on next step? Yeah. Epsilon s.
No, suppose that E is not equal to 0, That's x is greater than minus x3.
This is minus, sorry. Means here, what I've not highlighted in color, that is the electric field present over there. So everything is happening inside the depletion layer. Now write down step number 3 in N region. We should not write similarly. We have to derive it. For in N region, what is phi of s given by minus exponential of e of x dx? And what is e of x given by q nd na upon, so minus of minus it was positive q nd upon epsilon s. Here it will be x minus xn, right? Dx. So quickly solve this. Let's do this. This is a mechanical step now. So minus q nd epsilon s will come out. Inside you will get xn into x. Acha. If I remove this minus sign, so what this will be reversed now? This will be x into xn minus x square by 2 plus c4. Why I'm using c4? Because c1, c2 I've already used, c3 I've already used. Okay. Now how to find this c4? What you will write? How will you find c4? You will take x equal to xn. Wrong.
No, we'll take phi 0 at the limit.
Huh?
So like because we took phi of x is 0 at x is equal to, yeah, but that is different.
The problem is, see here, everyone.
At x is equal to
Electric field, how the electric field, diagram is like this. See, this is x equal to 0. This is minus xp. This is xn, right? And the electric field, how it is looking like this. Here it is 0. Yes or no? This is the neutral regions, which I am not showing. Now, if I extend it down and I plot the potential, how is the potential will be? Integration of this also. So you will get entire potential. This is distance x. So how is the diagram? Anyone? It is staying over here, constant. Here it starts falling down. It doesn't go to 0 over here. Where it goes to 0? Sorry, instance kick is not there. Here, then it falls 0, continues. Then it goes to 0 over here. Yes or no? So what is this? This is x equal to minus xp. We have already used that, right? This is x equal to 0. What this is? X equal to? Now tell me which boundary condition I'll use. This is N side, N silicon, this is P silicon. And this is what depletion region. Okay, now tell me. Can I say this potential is continuous? This is continuous, huh? This is. Is there a break over here or is it falling to 0? At x equal to 0, what is my potential? Is it falling to 0? No. We starting from x equal to minus xp, it's rising because of this falling down. देखो ये इसका integral है, right? So this is increasing, this is decreasing because negative sign है. Yes or no? Now, if this is increasing, they are saying it is constant now. Will it be 0 now? No. What will happen? It is continuous. So it will increase. And then it will go. So write down one line. Understanding this? What is the plot? This is psi of x. This is how it will look like versus distance. This one. So write down point number 4. Potential phi of x is a continuous function. Therefore, let's call this equation number 12, I guess. No, what do we call the other equation? Equation number 11 and 10 will be same. Correct, no? Why? Same, no? It should be same, right? So write down equation number 11, equation number 12 must be equal to equation 11 at x equal to 0. Yes or no?
Yeah.
So what should be C4 directly? C4 क्या C3 क्या मिला था? What we have got? QNA 2 epsilon s xp square. Are you understanding? Because it is continuous, whatever we have derived, it will be the same. Because it is the same equation. Okay, so C4 will be QNA upon twice epsilon s xp square, right? Are you following or you're getting confused? This is a continuous function. That's why we are writing this.
So we can also show that by using a plot from QP to QN, sorry, XP to XN, right? Because the plots are
XP to XN.
yeah, so the plots are supposed to meet, and then C4 and C3 are the same.
Yes.
Their XN will be 0 at this side, right?
Where?
Like when if you plot from this side.
But it's the problem with your justification is we are building up the voltage. Your voltage is getting built up. It's going from 0, it's rising up. So if I want to find exactly at x equal to 0, I should know how much is this point, which I don't know. I cannot solve it unknown, right? That's why we use the previous continuation. Here the same equation will be applicable ahead. It's the same curve. All right. So we use this and we substitute it over there. What do we get? Calculate now. Oh, sorry. Phi of x will be q and d epsilon s. Come on. X minus x xn minus x square by 2 plus q na upon twice is xp square. This is valid for 0 less than or equal to x less than or equal to xn. So this is valid for this region. Okay, this we call it equation number 13. All right, now written, completed. Now see over here. How much is this value? Can you tell me? How much is this value? It is same as the amount of band bending, which is VBI. So this voltage is VBI. Can I say at x equal to xn, my psi of x is equal to VBI built-in potential? Write it down. Point number 5. At x equal to xn, phi of x is equal to VBI. To substitute x equal to xn. Okay. Acha, this is formula for valid for what? N side, na? So this formula you have to substitute x equal to xn. So from equation number 13, substitute x equal to xn, what you will get? Phi of x equal to xn will be q upon twice is I am taking out. What you will get over here? Here you will get xn square minus xn square by 2. So half xn square, 2 is already out. Are you understanding? So what will be inside? Nd xn square, correct? Second equation, q upon 2 psi x out. So inside what do we have? Na xp square. correct? Because here x is equal to xn. Xp will remain as it is. So what you will get over here? Na xp square. And what we are calling this as? VBI. All right. This we call it equation number 14. So what do we, say now about the potential? The potential psi of x is variation against distance is a quadratic dependence on x, not linear. Is this a linear curve? Is this a linear curve? No, it's a quadratic curve. It's not neither an exponential, no? It's a quadratic curve. Okay, so the derivation for potential is over. Now we'll derive the last derivation, depletion region width, and we'll solve one numerical. So write down next derivation for space charge width. We know that space charge alternate name is depletion region. Space charge width W. It's not long. It's you will get it very soon. What is W defined as? If this is my PN junction, if this is x equal to 0, if this is minus xp, this is xn, what is W? This is W, right? This is P, this is N. Yes or no? So W is the distance of the space charge region extending in the P and N region. W is the distance extending space charge region or the depletion region extending in the P side or the N side. Can we start? Okay, so write the first point. We'll use one equation from the previous derivation. We invoke equation number 10. So write down from equation number 10. From equation number 10, we get, what is that? NaXP is equal to NdXn. Yes or no? So can we write XP as Nd upon Na into Xn? Yes. This we call it equation number 15. Okay. Now we substitute this in the VBI expression. What is that? Substitute this in expression number 15. So put value of Xn from equation 15 in to equation 14. So what do we get? We can directly write VBI na here. VBI is equal to Q upon 2 epsilon S. Here it is ND xn square plus, actually we are eliminating that xp term. So here what you will get? Na. What is xp square? Nd square upon Na square into xn square. Okay, write it down. Yeah, doubt? Nd square upon Na square into xn square. Following?
We can remove that NA.
Yes, yes, Na will go. And Nd we can take it this side. Okay, definitely we can remove one Na. So let's do that. Okay, so what do we get? VBI now? So VBI will be, yeah, we can take Q upon twice epsilon S. Can we take ND common? Xn xn square common, ND common. Okay, so what do we get inside?
1 plus ND upon ND.
Yes or no? Is that correct? So how can we simplify it further now? VBI is equal to Q upon twice epsilon S xn square ND. What do we get over here? NA plus ND upon NA. Yes? So basically we can rewrite it as VBI is, just I am reframing it, xn square ND upon NA into NA plus ND. Yes? This we call it equation number 16. Now, if I want to write xn in terms of everything else, see, everyone, understand, what is W? XP plus XN, correct now? So we are finding the expression of XP and XN. Are you getting it and adding them? So can I write in terms of XN this? XN equal to, what will be it? What will be XN equal to? Under root of na? So big square root of, what will come, tell me? 2 epsilon s into VBI upon Q. Here what will come? Reverse. Na upon Nd into 1 upon na? Correct. 1 upon Na plus Nd. Yes, this is correct. This has become longer. Yeah, this is correct. So call this expression. Okay. Yeah. So this will be Na upon Nd. Reverse now, because this will go up, this will come down. So this is one important relation X, and we have found out. Here we can write similarly directly. So write down similarly XP. Can you tell me what will be the difference? XP के लिए will be switching. NA and ND will switch. Rest will be same. VBI will remain the same. So it will be 2 epsilon S VBI upon Q ND upon NA into 1 upon Na plus Nd. This is the expression. This is equation number 18. So now total width will be xn plus xp, right? So W will be xn plus xp. Acha, which of the terms will go? Plus plus now, or it will add? Can I take in under entire square root? Can I add them? So how will I add them? How we will combine W or xn and xp? We can take common now. What we can take common? And then we can add the other terms. So let's do that. So W will be square root of, what will come? 2 epsilon s VBI upon Q divided by Na plus Nd. And inside the bracket, what you will have? Square root upon plus square root of is this correct? Yeah. Now now what do we do with this? Sorry, input value. Yeah, you can, but this can be simplified. I'll skip some steps. Finally, you will get this relation. Yeah, wait. For y'all will do it. See, it is this much into Na plus Nd upon Na Nd. This you will get at the end. Intermediate steps. You find out on your own. You're good at mathematics. Of course, you have to be in this subject. So this is equation number 19. You figure out how you do it and let me know if you get anything different than this. Na plus Nd upon Na Nd. Acha, here, what is VBI? Now don't break your head over there. What is VBI? What is VBI we have derived last time? VBI was Kt by Q natural log of Na Nd upon Ni square. This we have derived it last time. So write down where VBI is Kt by Q natural log of Na Nd upon Ni square. So this is the expression for W. So this is space charge or depletion region width of PN junction diode. Okay? Yes? I'll tell you even simpler formula. This is to this you have to remember 19 and this VBI expression for numericals. Completed up till here. This is to figure out how we can combine them and we'll arrive at this result only. Finally. You didn't understand how we got this? If you open the bracket, if you open this bracket, Na divided by, you will get the same thing. And combine. Yeah. You take it out and then take it in and then again take it out. If you take out Na and D, square root of Na and D, outside it becomes Na and Na plus Nd the whole square. When again you take it in, inside the first bracket you will get Na plus Nd again.
Then you only take out 2
Yes. Break. So I saved a few steps. Got it? Okay. Okay, next. Next. It's still not over. So you remember this equation NaXP dot NdXn. Yes or no? What is W given by? Xn plus XP. So here I'll substitute Xn plus, what is XP? Nd upon Na into Xn. Yes or no?
Yeah.
So W is Xn into, what is the relation? Na plus Nd upon Na. So what is Xn from here? Na upon Na plus Nd into W. Matlab, this is the formula. If you know the value of W, you can find Xn. Understanding? Similarly, how will you find XP? It will be Nd upon Na plus Nd. So these are some additional formulas which will come in handy while solving the numerical. I have written mod because, yes, it has to be positive. So these equations are equation number 20. 20. Next, derivation, you don't have it, but you can show it actually. That is your home assignment for, today. Homework is that we can show EM, maximum electric field, is given by minus 2 VPI upon W. You prove this, huh? This is equation number 21. I am not doing the derivation. Neither I am showing it. EM is the maximum electric field. What is VPI? Built-in potential. And W is the space charge width.
EM electric field.
I'll give you a document wherein all this information is there. You need to just refer it. Okay? Yeah? So in summary, we have, this was the PN junction. X equal to 0, minus XP, XN. This was P silicon, N silicon. How did we get the value of W? This was W. And if I plot over here, electric field, this was the electric field, right? This was W. What was the W given by? Square root of 2 epsilon VBI upon Q into, yeah, this is easier to remember this way. Then, you know what was the maximum electric field given by? Minus 2 VBI upon W. You know what is the area under this curve? Area under this curve is VBI, which is KT by Q natural log of Na Nd upon Ni square. You know what all these things tell you? This is a very powerful thing. That means you can control the width of the device. Let's say you're building a new device. So how will you control the width of the device? By controlling VBI, because Q is constant, epsilon S is constant. You can change the material. You can change the doping concentration. See? So W is dependent upon doping. So you can make a normal PN junction a Zener diode just by changing the doping. You can even change the built-in potential again by changing the doping. You can adjust the maximum electric field by changing again the doping. So NAND is under engineer's hand, process engineer's hand. All right.
So if we integrate the equation for W with limits XP and XN, we get VBI.
VBI we have written potential.
So we can integrate it with XP and XN as limits.
Okay. So numericals we will solve it next time. I want to show you all something. Wait.